This is a lesson on definite integrals. Corresponds to section 4-3 on page 265. So let's talk about the definition of a definite integral. We know what an indefinite integral is. We know an indefinite integral is the area between a function and the x-axis. Well, a definite integral is pretty much the same thing. However, as you can see in the picture here, it has limits. On this image, the area is S, and the limits are x equals A and x equals B. So let's get a little explanation of how this looks in a formula. Well, so this is the integral notation that we're very familiar with. The integrand and the differential, the f of x and dx, are exactly the same as with an indefinite integral. The only difference here is that we have limits of integration a and b, and those are noted on the integral sign. So if we do a sample problem here, we're going to be integrating from 1 to 10, 3x squared dx. So we're going to integrate it normally, of the 3x squared dx, and then we're going to evaluate it from 1 to 10. So we'll start by integrating it normally. We're going to get x cubed, and then we're going to evaluate it. So we're going to plug in the upper number, and then we're going to plug in the lower number, and we're going to subtract the two from each other. So we're going to plug in the upper number. It's going to be into x cubed. It's going to be 10 cubed, and we're going to subtract from that 1 cubed. We're going to get 1,000 minus 1, or we're going to get 999. So what exactly does that mean? Why does that work? Well, in this problem, really what we're doing is we're finding the area under the curve 3x squared from x equals 10 to x equals 1. So the 999 number is 999 square units is the area underneath that curve. But wait, what if, for example, we don't have the function in equation form? Or what if we're not able to integrate the function? Or what if we're told to use an approximation method? Well, we have a couple possible solutions. The first one we're going to talk about is geometric integration. In this graph, really what we're trying to do here, if we integrate, is find the area underneath the graph. And in this case, it's going to give us the total number of people if we integrate. And this is actually a 2010 free response question. They asked us to integrate. So what you're going to do here is you're going to use geometric shapes to try and find the area. And in this example, I integrated from 0 to 8. But obviously, it's very easy to accommodate a different limit of integration. You can integrate from 0 to 6, 0 to 4, 0 to 2 very easily. You just change the shapes that you're using. So the other option that we can use is Riemann sums. And there are 4 different types of Riemann sums we're going to look at today. A left sum, a right sum, a midpoint sum, and a trapezoidal sum. Let's note that we're going to use 4 subintervals for each of these, and we're going to be using the graph y equals x cubed. So let's focus in on the left sum really quick. Here you see the graph of y equals x cubed. Let's note that it's a overestimation if f double prime is negative, and an underestimation if f double prime is positive. So it's an overestimation if it's concave down, and an underestimation if it's concave up. So let's try and figure out what we're doing here. If we're trying to find the area underneath the graph, we know a couple different ways to do so. We know the area of a rectangle is base times height. So if we create rectangles underneath the graph, we can just find the area of those rectangles, and it'll be an approximate answer. So if we know the formula base times height, we can add the area of 4 different rectangles. Well, so we know the base is 1/2 unit. How are we going to figure out the height? Well, for a left sum, we're going to use the left side of each of those rectangles. So 1/2 times f of 0 plus 1/2 times f of 0.5 plus 1/2 times f of 1 plus 0.5 times f of 1.5. And we're going to get an answer of 2.25 square units as an approximate area underneath that graph. Well, if we switch to a right sum, we need to know that it's an overestimation if f double prime is positive, and an underestimation if f double prime is negative. So it's an overestimation if it's concave up, and an underestimation if it's concave down. But essentially, we're doing the same exact kind of thing. We're using the same formulas for the rectangles. This time, our heights are just going to be the right sides of each of those triangles. So f of 0.5, f of 1, f of 1.5, and f of 2. And here we're going to get an answer of 12.5 square units. Now, if we look at a midpoint sum, again, we're doing exactly the same thing, except our heights here are going to be the midpoints of each of them. So we're going to use f of 0.25, f of 0.75, f of 1.25, and f of 1.75. We're going to get an answer of 3.875. Our final option here is trapezoidal sum, and I'm going to talk a little bit about this one. The formula in the textbook for trapezoidal sum is very rigid. It assumes that your subintervals will all be of equal height, and I don't think it's worth using, as heights are often different within the same problem. So the textbook example will work on this example because the subintervals are equal, although it's not very common to find this on the EP test. So we know that the area of a given trapezoid is 1/2 times the sum of the bases times the height. So we can just take the area of 4 different trapezoids and add them together, similar to what we were doing to rectangles, but we're just going to use trapezoids this time. And we'll just use this equation here. We'll solve it out, and we'll get an answer of 4.25. So let's take a look. How'd we do? Well, if we plug this into the calculator under the Math 9 FNINT menu, we'll get an answer of 4. Note we plug in 0 and 2 in the calculator manner in the opposite way that we would plug it in when we're solving the problem out by hand. The lower limit goes in first, followed by the upper limit, whereas when we're doing it by hand, the upper limit goes in first and the lower limit goes in second into when we're evaluating it. So let's figure out how the calculator is actually doing this. Well, the calculator is really approximating the answer for us. It's breaking up the area under the graph into very small sections and finding the area just like we were, although it's using smaller sections and doing a lot more calculation than we were. So the only actual way to figure out the area underneath the curve, or what the integral would find, would be to integrate by hand or to use a geometric method. So the left sum was an under approximation here. The right sum was an over approximation. The midpoint sum was an under approximation. And the trapezoidal sum was an over approximation. Generally speaking, the trapezoidal sum is the most accurate and closest to the calculator's answer, or the actual answer, and the left sum and right sum are the least accurate. And there's quite often a little bit of disparity in those answers, because one is either a very big overestimation or one's a very big underestimation. So I hope you guys have found this PowerPoint very helpful, and good luck.